Okay, the first problem here says which of the following is not true of Mendeleev's periodic table. Okay, and so this one is a fairly easy one because we're just looking at the difference between you have Mendeleev and you have Moseley, and if you notice, and this is just something you're just going to have to go back up and look, but on this one the answered choice here should be B, and that's just because it was later that they started organizing the periodic table by atomic number. Prior to, I believe it was Moseley, you have to look that up, I'm not 100% sure, they were using, the periodic table was set up based on the atomic mass, chemical properties, and based on that they used it to determine your undiscovered elements there, okay? Alright, number 13, it says, compound has a molecular formula, okay? Which of the following is the correct empirical formula for the compound? So remember that your molecular formula, I could give you another molecular formula here. I could say C6H12O2, okay? This is just a multiple of this, okay? If I multiplied everything here by 3, I would have C9H18 and O3, okay? All of these, when you reduce them down, they're going to give you C3H6O. This one I cannot reduce down any further, and so in this case this is the empirical formula here. These are molecular formulas there. Alright, so your answer choice here would be A on that 13. Let's look then at 14. Okay, here we go. It says during the chemical reaction you get 36.8 grams of aluminum and 36.8 grams of HCl were allowed to react. Determine how many grams of excess reagent are left over after the reaction. Okay, so for both of these you can either go gram to gram, you can go gram to mole. We're going to go gram to mole. Alright, so I'm going to take 36.8 grams of aluminum, and in this case, let's see what it says. Determine how many grams of excess. It doesn't matter which one of these you convert it to, whether you convert it to aluminum chloride or whether you go to hydrogen gas, but you just got to pick one of them. Okay, I'm going to go to hydrogen gas because I think that's a little bit easier. Alright, so I need my periodic table, which I don't have. You're going to have to give me a second to get it. Okay, so you're going to use your periodic table and you're going to look and you're going to see that, oops, that's upside down. You're going to see that aluminum, which is right here, is 26.982, I believe, grams, okay? So I'm going to say 982 grams of aluminum for every 1 mole of aluminum. And then I need to say that in my balanced equation I get 2 moles of aluminum. This is your ratio, right? And we're converting to hydrogen for every 3 moles of that. Okay, so we're going to figure out, in this case, this is going to get us the moles of our hydrogen. So when we do this, we're going to get, I don't think you guys can see it. Alright, so I have 36.8 times 3. Whoops, what did I do? 36.8 times 3. Alright, times 3, and then I'm going to divide this by 26.982 times, what do we have? 2. Because remember, we multiply everything on the top and divide by everything on the bottom. Okay, so here I'm going to carry this out to as many significant figures as I can. So this is going to be 2.0458, and this is moles of H2. Okay? Alright, so you can see it written there. So now my next calculation is to say that I've got 36.8 grams of HCl, and I want to convert this also to H2. So I know for every 1 mole of HCl, I have hydrogen, which is 1.008, plus my chlorine, which is 35.45. Where is it? Chlorine. 3. Okay, and again, both of these come from your periodic table, so you can see chlorine right there, the value for it, okay? Alright, so this is my molar mass of it, and this is going to be 36.461, and this is grams. Look at my balanced equations. So now I've gone from grams to moles. Now I need to go from moles of one compound to moles of another. So I need my ratio from the equation, so we get 6 moles here and we get 3 moles here for your H2 gas. And in this case, so I'm going to take 36.8, multiply that by 1 times 3. I get a number, then I'm going to divide this by 36.46, 1 times 6. And remember, make sure you keep the top and the bottom number separated. So this is 0.5046, we'll carry that out, okay? Oops, sorry, you can't see that. All right, and again, these are moles of H2. Okay, so what this is telling me is if I have 36 grams of HCl, I can only make 0.5, so about half a mole of my hydrogen gas. Or if I have 36.8 grams of aluminum, I can make 2 moles of my hydrogen gas. Well, I only have enough HCl to make 0.5, right? So my limiting reagent, so your limiting reagent is going to be your HCl, right? So now my excess obviously has to be the aluminum. So how much excess is there? Well, so what I have to do now, you have to take the 2.0458 and you have to subtract from that the 0.5046 moles, okay? That's going to give you that's the excess moles that you have, right? So this is going to be minus 0.50465. Okay, so this is 1.54115. All right, those are the moles. This is a long problem, okay? So those are the moles of H2. Now, I need to now convert this back to grams because they ask you for grams of excess reagent. All right, so I know that I have 1.54, can you all see that? Okay, 115 moles of H2. I know from the balanced equation that for every 6 moles of HCl, that's wrong, sorry, I'm wrong. For every 3 moles of H2, I have 6 moles, oh crap, I'm really screwing up right now. This is 2 moles of aluminum, okay? Because remember, I'm going to excess reagent, and the excess reagent we said was aluminum. Alright, so I need for down here, I need every 1 mole of aluminum, so I need the molar mass, right? This is going to be 26.982 grams. Alright, multiply everything on the top, divide by everything on the bottom, so I'm going to keep that number there, multiply this by 2 times 26.982. Alright, so multiplied everything across the top, divide by the bottom, which is 3, and I get 27.7 grams of aluminum. And if we go back here and we look, answer choice number A, or letter A, is your answer. Alright, let's go to number 15. It should be a little bit easier. Okay. Using a solubility table, determine which compound is soluble in water. So let's go to our solubility table. If we're looking at our solubility table, we look for your hydroxide. If you go here to hydroxide, this is on the back of your periodic table, we know that all your hydroxides, oops, you can't see it, compounds are insoluble. It tells you here that it's insoluble unless it's with ammonia, group 1 metal, that's your alkali metals, calcium, strontium, barium. It is with magnesium, so this is not an answer choice. Alright, let's look at strontium, sulfate. So we go to our sulfates. Okay, where's sulfate? There it is. All of these compounds are soluble, okay, is what it says. So it's going to be soluble unless it's with strontium, barium, lead. We see this with strontium, not an answer choice. Alright, let's look at chlorine. Right here it says chlorine. All of your chlorides are soluble unless it is with silver, lead, or mercury. This is with lead, so that's not a case. So we're going to look at our chlorate ion. We look here, no exceptions. Answer choice is D. Here we go. Copper is a soft metal, allowing it to be molded into different shapes. What is the term describing the ability of a metal to be pulled into wires? Okay, we know the density is mass over volume. Not it. Diffusion. This is when water molecules go from basically they go from a higher concentration to a lower. Well, it's not just water. I guess it's a lot of different. It can be anything, right? Higher concentration to lower concentration. Conductivity, we know, is the ability to conduct electricity. So again, we talked about copper being malleable and ductile. Ductile is the ability to be pulled into wires. Alright, we are done with that page. Alright, 17. says argon is highly unreactive element. It's highly unreactive because it is in which group? It is in group 18, right? We know these to be our noble gases. Based on the periodic table, which of the other elements would you also expect to be unreactive? So let's look at our periodic table and what we know. And basically this question is asking you, what do you know about trends? We know that everything in groups acts the same, right? So that means that if we're talking about, what did we say? We said argon. Well, what else is in this? Well, we see Kr, which is krypton, and so your answer choice needs to be C on that one, okay? All right. This says select the type of bond which should be, let's see, connect the two carbons in the structure. Okay. So what they're showing you here is that, okay, you might not be able to see this very well in the video, but there's 2 electrons here and there's 2 electrons here. We know that 2 electrons equals 1 bond, okay? They're showing 4 electrons in between these 2 carbons. So if this is 1 bond, this is a second bond, this equals 2 bonds. We know this to be a double bond. So your answer choice is C. Alright, let's look at number 19. It says using the solubility graph below, determine if a solution is saturated, supersaturated, or unsaturated. So we're going to go over here, we're going to look at sodium nitrate. They tell you that it's this one right here. Oh, sorry, you can't see. And it says we need to look at, what does it say? Solution with a temperature of 80 degrees and a solubility of 10 moles per kilogram. Alright, so what I'm going to do, I'm going to go here to 80 degrees. I'm going to draw this line up until I hit this point right here, okay? So it says that it has a solubility of 10 moles per kilogram. Well, if it was 10 moles per kilogram, it would be right here, okay? So the fact that it's a lot higher than that tells me that this should be a what kind of solution? Hopefully you guys remember this. In this case, it is a, why do they say unsaturated? Of 80 degrees. Oh yeah, sorry, I'm stupid. Okay, so it's at this says that you've got 10 moles per kilogram. So here's where you are. If it was a saturated solution, it would be up here. So since it's below that point, that means that this is an unsaturated, so that's A. Okay? Wow. I got a little confused there. Okay. Let's see. Based on the trends in the periodic table, which of the following elements would be expected to have the largest atomic radius? So if we go back here and we look at our periodic table here, we know that this one has, this number tells us the number of protons, it also tells us the number of electrons. Remember, this number right here tells me the valence electrons, but this is the total number of electrons. As you go down this group, what do you notice? You notice that we get more and more protons, we also get more and more electrons. Well, if I get more electrons, what happens to the size of my atom? It has to get bigger, right? Because we have to continue to add and add and add electrons. So it says, which of the following elements would be expected to have the largest atomic radius? So if I'm looking at this, obviously because this has more electrons, it's going to be further and further out, right? So it has to be iodine. Answer choice A. Which of the following is an example of a fusion reaction? Okay, remember fusion, okay? This is when you fuse something together, you take 2 small things, okay? So I take these 2 small things and I put it together and I get a bigger one, okay? When we talked about fission, okay, this is when you take a large one and it breaks down. Oh, you can't even see what I'm writing. Fission is a large one and it breaks down into smaller compounds, okay? But fusion, fuse, okay, we put 2 things together, okay? So obviously splitting, that is not a good answer choice for what we're doing here. Emitting a beta particle, okay? If it emits a beta particle, then that's going to be a beta reaction, usually, not always, okay? But in this case, tritium, which is a small one, and deuterium, which is a small compound, so this is H3 and this is H2. This right here is going to give me helium, right? 4, 2 plus a neutron. Alright? So in this case, our answer choice is going to be D. Because again, these are 2 really, really small molecules, okay? And I just drew them out there for you. Alright, 22. And it says an experiment is performed to test how agitation affects the solubility and rate of dissolution of sodium chloride in water. All trials were performed by placing 50 grams of sodium chloride in 1 liter of water at 25 degrees C. What conclusion can be drawn from the table? Well, so if I'm looking at this table, right, this is telling me, it says the amount of total solid that is dissolved, okay? So in trial 1, what they did was they took it and they shook the solution, right? And they said that since we put 50 grams in 1 liter, okay, they said the amount that was dissolved, 50 grams was dissolved, okay? Now, if they didn't shake it, okay, so they're telling you that 50 grams dissolved, but look how much more time it took. This only took 60 seconds. This took a minute. This took 43,000 seconds, okay? You can divide that by 60 and figure out how many minutes it is, okay? And so in this case, this is telling me that when I shake it, things dissolve better, right? And so what's another word for shaking it? Obviously, it's agitation there, right? So agitation does not affect the amount of sodium chloride. Well, we see shaken, not shaken. We see a difference, so that's not an answer choice. Sodium chloride dissolves faster when the solution is not agitated. Well, this is not agitated, and we see that it takes a lot longer for this to dissolve, right? Not an answer choice. Agitation decreases the amount of sodium chloride that can be dissolved. So the more we shake it, we decrease the amount that can be dissolved. But that's not what the data shows. The data shows that 50 grams dissolved in 60 seconds. Here, 50 grams, when we did not shake it, dissolved in 43,000 seconds. Okay, so this is not an answer choice. This one says a greater amount of sodium chloride can be dissolved when the solution is agitated. So when you shake it up, more dissolves. Answer choice is D. 23. Select the correct chemical formula for the following base. Base, okay, so we know that bases typically have hydroxide, OH minus, okay, we just learned this. Automatically, I can cancel out this first one here, okay? Oh, and it says here we got hydroxide, so that's the other reason I can cancel that out. It also says potassium. All right, P. Don't make this mistake here. P means phosphorus, okay? So your answer choice here, potassium hydroxide, has to be C. And you can use your periodic table for this. All you have to look up, here's K, that tells you it's potassium. You come over here, you see P, that's phosphorus. This is not one that anybody should miss, okay? All right, let's look at number 24. 24 says, what is the mass, here we go. What is the mass in grams of 9.86 times 10 to 24 molecules of methanol? All right, they give us molecules, and we need to get to grams. So we got to use a couple different things. First of all, we're going to need Avogadro's number. So we go molecules, and I need to go molecules to moles, because remember, we always have to get to moles first, okay? So I know there are 6.02 times 10 to the 23rd molecules for every 1 mole. Okay, and I know that for every 1 mole of C3OH, so for every 1 mole of methane, oh, you can't see it, sorry, we got to figure out the molar mass. Well, how do you figure out the molar mass? I'm going to come over here and I'm going to say carbon is 12.01. So I got 1 carbon, and I've got 4 hydrogens, each of those at 1.008. and 1 oxygen at 15.99. Now, the one thing you guys want to make sure that you do, okay, make sure, oh, you can see my face in there. Don't round off anything till the very, very end, okay? All right, so here we go. Carbon, which was 12.011 plus 3 times 1.008, because remember, again, we had 3 hydrogens, plus 15.999. Alright, and we get 31, so my mass for, again, the molar mass for your methanol, 0.34 grams. Alright, so now we're going to multiply everything across the top. We're going to divide everything by the bottom. Now, anytime that you guys have these big values here, you need to make sure that you put everything in parentheses, okay? So, I'm going to take this value and I'm going to multiply it by whatever's on top. We have 1, and we also have 9.86 exponent, or you can do times 10. If you do times 10, make sure you put this in parentheses first, okay? You can add exponent. E means times 10. Put 24. We get this answer here, right? Now I'm going to divide it by, and so I'll show you the other way if you're not using exponent. You're going to go 6.02 times 10 caret 23. Make sure you put this in parentheses, and we get 508. Oh, Did I do something wrong? It's not an answer choice. Yeah, 24. Well, you guys can figure it out. I'm not going to take the time to go back. I must have typed in something wrong. Let me see. Oh, I can't go all the way back. Well, anyway, when I'm looking at this, it's really close to answer choice B, and I know that answer choice B is correct. So you guys can go back and work that one out yourself. I don't spend the time to do it. Okay. What's next? 25. Which statement comparing alpha radiation, gamma radiation is or are correct? Okay. Alpha radiation, remember your alpha particle is helium particle, or you'll see it written like this. And then a gamma particle looks like this. Remember, alpha, because it has mass, and this is mass here, right? This 4 and this 2 tells you that there's some mass to it. 0 and 0 tells you there's no mass. This one's going to be a lot heavier. It's not going to travel as far, right? If you think about the difference between throwing a bowling ball and like this is like a golf ball, okay? It's really small. So it says gamma radiation is not attracted to electrodes, while alpha radiation is attracted to negative electrode. And so if we look at this, this has no charge here. Typically your alpha particles are going to have a positive charge, okay? So it says gamma radiation is not attracted to electrodes, while alpha radiation is attracted to the negative one. This statement can be true because we know that your alpha particles are positive, okay? So these are positive, right? This has no charge, so it's not going to be attracted to anything. Gamma radiation is less penetrating power than alpha radiation. This is true because gamma particles are really, really small. They have no mass, okay? These are the ones that are really dangerous. They'll go all the way through your skin, okay, and everything into your organs. Alpha particles, we can stop with a sheet of paper. So this statement is true. Gamma radiation is visible while alpha radiation is not. I don't know if this is true or not. I'm going to assume, well, I'm not really 100% sure, but since I think these two answers are correct, on number 25, no, is this one correct? Hold on. Gamma radiation, oh, I'm sorry, I'm wrong. Alpha radiation has less penetrating power, right? So these two are switched. Gamma's going to penetrate a lot further than alpha, so this answer is wrong, and then this one is wrong, so that means that your answer choice has to be A. Alright. What is the molecular geometry of this compound here? Alright, so here we go. I've got carbon that has 4, okay? I'm going to put, I have an oxygen that's got 6, okay, so I'm going to put that it's going to share 1 here, and then it's got here, and there. I'm going to put a chlorine here, and then I'm going to fill in the rest of the 7 or 6 that it has as 1, 2, 3, 4, 5, 6, plus your 1 here, your electron. Again, chlorine, 1, 2, 3, 4, 5, 6, 7, so it's sharing there. Now, here's what's going to happen. Oxygen, it's sharing one of its electrons there. It still has one more electron that it needs, because right now you can see that it only has 7. Your carbon right here only has 1, 2, 3, 4, 5, 6, 7. So if this comes in here and this bond's there, we're going to end up forming a double bond, and so what your compound will actually look like will be like this. And this is going to be a double bond here with your oxygen, okay? Now, here's what we notice. Around your carbon, because remember, when we're looking at molecular shapes, you can't see, we have to look at what is around the carbon. So this has 1, 2, 3, 4 bonds, okay? But remember, we count this double bond. So basically, this is a double bond here, we have a bond here, and we have a bond here. Remember, we're going to count this double bond, even though there's 2 here, we're going to count it kind of like a single bond. So we've got 1, 2, 3. No lone pairs, and again, this is on the central one, so that's going to tell me that this is going to be trigonal planar. Okay? Alright, let's look at number 27. Alright, this says, during the reaction below, methane gas reacts with water vapor to produce carbon monoxide. Determine how many liters of H2 are produced when 49.8 liters of gas is reacted. Okay. So we're going to start here. We're looking at 49.8 liters of CH4. This tells us it's STP, so remember, you can use for every 1 mole, there is 22.4 liters, okay? So then it's only because it's at STP. So I know that if I have 22.4 liters of CH4, I've got 1 mole of CH4, okay? And they want us to find what? We're looking for liters of H2, okay? So now I got to use, so now I'm at moles of CH4. I need to use the mole to mole ratio from the balanced equation. So I have for every 1 mole of CH4, right? I get, what am I looking for? H2. I get 3 moles of H2. My next step now is that for every 1 mole of H2, I get 22.4 liters of H2. Alright, so when I put this in the calculator, now I'm going to do something to simplify it, but if you want to multiply across the top and divide by the bottom, feel free to do so. But I got a 22.4 on top, I got a 22.4 on bottom. I'm crossing those out. I'm not even going to put that in there. Alright, so I have 49.8 times 3. 49.8 times 3. And then I'm going to divide this by nothing. You're going to get 149.4, and so my answer choice is D. Come in. Oh, you can't come in. All right, I'm going to pause for right now.